This video is going to be about inverse quadratic interpolation. It will present the basic mathematical ideas behind the derivation, the convergence, and also the advantages and disadvantages, and also in comparison between the other methods. So let's begin with a brief description of the inverse quadratic interpolation method. So an inverse quadratic interpolation is a root-finding method that we can interpret to be a resulting method of the secant method. So let's have a look at the numerical derivation of the inverse quadratic interpolation. So we have these 3 points, which are our initial values. Respectively, we will get the following result, where f is a function. And we will let g be an inverse of f. So fitting the points into a parabola in y, we can compute the polynomial interpolation with Lagrange basis functions, giving the following result. So to obtain the estimate for the new root x of n plus 1, we will let y equals 0 for the equation that I've shown before. Therefore, we will obtain this new result. And this will be the formula used to obtain values that will tend towards the solution. So we will use this new point to replace the furthest outer line of the 3 initial points that we had initially, and we keep on repeating this procedure until the error is acceptably small. So now let's look at the convergence behavior. The convergence for the inverse quadratic interpolation method is asymptotically faster than the secant method, but the method can become very poor if the initial values are not picked close enough to the solution. This is one major disadvantage to the inverse quadratic interpolation method. With this concern of stability, if the initial values aren't picked correctly, the inverse quadratic interpolation method is usually used alongside other methods. For example, Brandt's method. So Brandt's method is a root-finding algorithm which combines root bracketing, bisection, and inverse quadratic interpolation. And Brandt claims that this method will always converge as long as the values of the functions are computable within a given region containing a root. Therefore, since this method is quite similar to the secant method, the order of convergence can be evaluated similarly to the secant method by letting xn equals s plus epsilon n, where s is the solution and where xn will tends towards the solution s when epsilon n tends towards 0 as n tends towards infinity. So subbing xn into our inverse quadratic interpolation formula, xn plus 1, and using Taylor's formula, we will be able to evaluate the order of a convergence to be 1.8392. Computations are omitted from this presentation because the evaluations and the workings are quite similar to the secant method. That was already discussed in the lectures. To further demonstrate the convergence behavior, let's look at an example. So for this example, what we have to do is we have to determine the least positive root of this function, f of x, presented here. So firstly, let's have a look at the function visually. So to plot the function, we just let f of x equals 0. Here I've used Maple to plot the graph. Now I'm only focusing on the positive side, so that's for this graph only shows the positive root of the function f of x. So we can see that the positive root lies within an interval from 0 to 2. So therefore we should pick initial values that is within this interval so that we can make sure the inverse quadratic interpolation method will converge and is stable. So let's pick our initial values to be 0, 1, and 2. Next step is to evaluate our y values. So if we just input our initial values back into f of x, we will obtain the y values. And therefore, our initial values are the following. Now, to make sure that we will have convergence, let's plot this, our parabola that we will be fitting, and make sure that it will cross the x-axis. So to do so, we have to plot g of y. So substituting these initial values into our function g of y, like so, and plotting the graph, we can see that g of y will intersect the x-axis. So we can continue on with this method. So the next step is to compute x of n plus 1, so x of 3. And we do so by inputting our initial values into the formula x of n plus 1, like the following. So using simple algebra, we can evaluate that x of 3 equals 1.255 approximately. And upon substituting the value back into f of x, we will obtain the value for y.